We've talked about reactions and how to balance them, how to identify what type they are. Some reactions, though, are reversible. That means they could go forward, but then you could reverse them to go backwards. Now, some can't be reversed because at least one of the reactants has been completely used up. And then the reaction stops. Think of this like a train stopping with passengers getting on and off. There are always people getting on and off the train, but especially if you're a big city, people get off, people get on, but at the end of the day, the train completely stops. And that would be one that isn't reversed because it completely stops. But there are lots that are always reversible. People are getting on and off and on and off, and it's going both ways, both directions. Now, equilibrium occurs when no net change occurs in the amount of reactants and products. It occurs when the products and reactants form at the same rate. So at the beginning, you're not in an equilibrium. You have all the reactants. So at the beginning, you have all the reactants, and you don't have any products at all. But you start to have products, but you don't have as many at first because you have a lot of these reactants. But slowly, if this is your scale, slowly you start getting more and more. And as that happens, you become more balanced until the rate is happening at the same time. You're going forwards as you're going backwards. It doesn't necessarily mean you have this equal amounts of product and reactants. It means that you have constant rates of you have constant rate of product to reactants because it's gotten to be at the same rate where you're forming reactants or as you're forming products. Now, in equilibrium, you never have reactants that are completely used up because they're constantly being formed from products. Now, equilibrium is shown using double arrows. So if something's in equilibrium, it'll look like this. A plus B equals C plus D. So if it's in equilibrium, it's going back and forth. And that's why you have those double arrows. And the rate is determined by how quickly the reactant disappears. So how quickly the reaction occurs is measured by how quickly the reactant turns into products. Equilibrium, like I said before, doesn't mean the same amount of products and reactants are present. It just means they're forming at the same rate. You don't have any net change occurring. It looks like the amount that's there is fairly consistent. Most reactions favor either the formations of products or the formation of reactants, whichever is more stable. And some reactions show it as something like this. Like if this arrow to the right is bigger, it means the forward reaction is favored. The formation of products is more favored than the formation of reactants in the reverse. There was a French scientist called Henri Le Chatelier, and he proposed that disturbing equilibrium will actually make a system adjust to regain that equilibrium. And this is called Le Chatelier's principle. And companies actually use this to increase their yield. And they've learned how to manipulate equations that are at equilibrium to continue to produce to maximize their profits. Ammonia production, for example, is one of these in the Haber-Bosch process. Ammonia is actually really important for our economy because our farmers depend upon that as a form of fertilizer. Before that, you couldn't have any manufactured fertilizer. You had to get it from your cows or your horses or in the form of manure. And you couldn't just put straight manure on there. You had to let that manure age. So there was quite a bit of process that if you didn't have any animals or your neighbors didn't have any animals and you needed fertilizer, you were struggling to get the nitrogen back into your soil. So this ammonia process that was invented by Haber and Bosch really revolutionized agriculture. If we look at equilibrium, and this is calcium carbonate, and it's in equilibrium with calcium oxide and carbon dioxide. If we remove the gas, the carbon dioxide, in the reaction will continue to move to the right to reestablish equilibrium because it says, wait, I'm not in equilibrium anymore. I have to reestablish this. So it's going to adjust to try to balance out that amount again, that reaction. Now, with an equation of all gases, and if you change the pressure, the equilibrium will shift to the side with the fewest number of moles. It's like saying, I have 5 people in one room and 10 people in another. Which room are you going to go to? It's going to shift to the room where there are less people because it'll have more room. That's basically what happens with the gas. If you have an energy change as part of the reaction, or if you want to add more reactants, what will happen to the reaction? Think about a teeter-totter or a seesaw. They're the same thing, but different regions call them different terms. So you want to be balanced, but you just added more reactants. Remember, reactants are on the left side. If you add more weight here, it's heavier on the reactant side. So what way does the reaction need to go in order to balance that reaction out? We need to add more on the right. So the reaction would shift to the right to make more products. Energy is part of every reaction. So if you added or removed energy, that would also change the equilibrium. For example, we have N2 plus 3H2 produces ammonia in the gaseous form plus energy. So here we have, again, if we see energy as a product, what happens if we add more energy? So it's like this. It's all balanced, but I'm going to add energy. Energy is on the product side. So I'm adding more weight to the right side. So now my teeter-totter looks like this. What way do I need to push? What side needs to have more added in order to balance it out? We need to push this down, so we need to move it to the left. So this way, if you add more energy, you're going to reverse the reaction. This is what happened if you added energy. Think of equilibrium as a teeter-totter. So here we have this reaction. And what happens if we increase the temperature? So the temperature gets hot. Remember, we had our teeter-totter. We're increasing the temperature. Which side is going to be heavier? The product side is going to be heavier. So which way is it going to be pushed in order to balance that out again? The push to the left. So that would be B. The reaction shifts to the left. I want you to try 2 and 3 on your own. And then join us to see how you did on them, to see if you answered them correctly. All right, so let's look at 2. We have this equation. SO2, 2SO2 plus O2 produces 2SO3. So sulfur dioxide plus oxygen produces sulfur trioxide. What happens if we add more sulfur dioxide? Remember, we're here, we're balanced, but we've added more sulfur dioxide. Sulfur dioxide's on the reactant side. So the reactant side's heavier. So what's going to happen to the reaction? It's going to try to get rid of all that extra by making more product and pushing it to the right. So the reaction shifts to the right. Like I said, I'm a visual person. I use the teeter-totter method to help me. If it helps you, great. If you could do it without visualizing it and writing it down, that's great too. For number 3, for the reaction, phosphorus trichloride plus chlorine gas is in equilibrium with phosphorus pentachloride. Everything is a gas. What effect does decreasing the volume of the container have? If you're decreasing the volume, think of a balloon. If you push down on the balloon, you're increasing the pressure. And on the slide, 2 slides previous to this, we know that if you increase the pressure, equilibrium shifts to the side with fewer moles. Okay. So let's look at this. Well, the moles are basically the coefficient. The coefficients tells us how many moles of each we have. So on the reactant side, we have 1 plus 1, which equals 2. And on the product side, we only have 1. So we have 2 moles over here on the reactant side and 1 mole on the product side. So if we're adding more pressure to decrease the volume, which way is it going to move? It's going to shift to the right toward the side that has fewer gas molecules. I want you to try these and then come back after we've reviewed them, or come back after you've done it so that you could see as we review them if you got them correct. Now, in the reaction, carbon plus water is in equilibrium with carbon monoxide plus hydrogen. We're in equilibrium. If we remove hydrogen gas, we take this out, what's happening? What will happen to the system? So hydrogen is on the product side. So the product side is going to be lighter. So which way is the reaction going to shift to reestablish equilibrium? It's got to shift to the right. Because if it's making more product, it has to replace what was taken out. For the exothermic reaction, nitrogen dioxide is in equilibrium with dinitrogen tetroxide plus heat. What change favors the formation of more NO2? So we want to make more NO2. If we took out the heat, what would happen? Would we make more NO2, or would it try? If we took this out, it's just like doing this here. So it's not decreasing temperature. If we removed NO2, so if we took NO2 out, it would try to replace what was taken out. So yes, removing NO2 is what would happen, because if we took NO2 out, our teeter-totter would look like this. And so the reaction would shift this way. Now, reaction rates occur in every single reaction. And every reaction actually needs what's called the activation energy. This is the amount of energy that particles must have when they collide to react. This is what activates the reaction, hence it's called activation energy. All reactions require activation energy. Now, to determine the rate or the speed a reaction occurs, you're going to measure how quickly one of the reactants disappears or how quickly one of the products appears. And rates are really important. And if you don't think so, have you ever looked at an expiration date on your milk or on your eggs or any other food product? The expiration date is determined by the rate of the reaction. So these are really important in our lives. Here we have an example of our reaction occurring. You start with a certain amount of energy, and the difference between the amount of energy added and the original energy of the reactants is your activation energy. So right here, you can see this right here is your activation energy. And this is the energy of your products. Not always is it this way for the reaction, but you will always have an activation energy. You will always have to have some amount of energy added to the system, to the reaction, in order for it to get started. For a combustion reaction, you're adding a little bit of heat to get it started. Now, 4 things will affect the rate of the reaction. Temperature. Most reactions speed up with increasing temperature, like your milk spoiling. Again, why reaction rate is important. Concentration. The amount of the substance present in a certain volume. If you increase the concentration, it increases the rate. Now, sometimes in a reaction, you have more of one reactant is available than another. And the one that there is not enough of is called the limiting reactant. And that's because reaction can't go forward once it's used up. It stops the reaction. If you run out of a reactant, you can't continue the reaction. A third thing that affects the reaction rate is a catalyst. A catalyst is a substance that speeds up the rate of a reaction without being permanently changed or used up itself. It does change the rate by lowering the activation energy because it binds the reactants together. So it doesn't have the reactants don't have to bounce around and try to find each other. They have like a plate for everything to happen on. Your catalytic converters in your cars are dependent upon a catalyst. That's why they're called a catalytic converter. It helps the process go much faster than it would without the catalyst. In our bodies, we depend on catalysts. We have enzymes and proteases. Enzymes are biological catalysts. Proteases are specific types of enzymes that break down proteins. We also use those in meat tenderizers and in contact lens cleaning solution to break down the proteins from your eyes that have gotten onto your lenses to clean them off so that you have clearer vision. If you did not have these enzymes in your system, if you didn't have this specific protease, for example, that would break down protein, you would have a lot of health issues because you would not be able to get the nutrients that you needed. Now, sometimes we want to slow down reaction, and we use inhibitors. Now, you might think, well, why would we want to slow down a reaction? Well, we might want to stop viral reproduction. Because we want to get rid of this virus. So if we don't use antiviral medications, which actually inhibit viral reproduction, then we're not going to be able to fight it as easily. So yes, we use inhibitors. Anesthesia is a type of inhibitor. And predators that have poison, they use inhibitors in their poison to kill their prey. Antibiotics, they're like antivirals. They'll stop the reproduction of bacteria. And herbicides and pesticides are also types of inhibitors. So we have many different applications that we don't realize in our lives each day that we use. All right. That is it for this week. We'll see you next time.